Today we're going to combine a little of geometry trigonometry with algebra 2 trigonometry, mostly right triangle stuff. We know in a right triangle that the hypotenuse is always opposite the right angle, and then we've got angles that we determine. In this case, here's our angle theta, and relative to angle theta, this side directly across is called the opposite side, and the side directly next to is the adjacent side. We don't call the hypotenuse necessarily a side, we just call it the hypotenuse. Now, from geometry, we know that the sine is equal to the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Now, it's also true that the cosecant is the reciprocal of the sine, so it's the hypotenuse over the opposite, where the secant is the reciprocal of the cosine, or the hypotenuse over the adjacent, and the cotangent is the reciprocal of the tangent, or the adjacent over the opposite. It can also be said that if the cosecant is the reciprocal of sine, then sine is the reciprocal of the cosecant. And likewise for cosine and secant and cotangent. Now, if we know that the side C is 13 and the side A is 5, and we want to find the cosine of angle A, so this angle here, well, we know the cosine is the adjacent over the hypotenuse, so the cosine of A is the adjacent side, that's the side next to, so that's equal to B over 13. Now the problem is we need to find B in order to find the cosine value, and luckily we have a right triangle, so we have a Pythagorean theorem we can set up. We can say that we know a squared plus b squared equals c squared in this case, and we know that 13 is c, we know that 5 is a, and we're looking for b squared. So we can say that 169 minus 25 is equal to b squared. B squared is equal to 12, I'm sorry, 144, and b is equal to 12. So the cosine of a is equal to 12 over 13. And that's our answer. Likewise, in this case, we know that side C is equal to 7 and side A is equal to 3, and this time we're looking for the cosecant of B. The cosecant of B is equal to the reciprocal of sine, and sine is the opposite over the hypotenuse. So this is the hypotenuse over the opposite. And fortunately, we have values for both of those. So we have 7 over 3 is equal to the cosecant. Now, in any case you're trying to find Pythagorean values, there are some Pythagorean triples that you should have gotten in geometry, but maybe not. And if you didn't, here are some nice Pythagorean triples that always work out cleanly. There's the 3, 4, 5, the 5, 12, 13, the 8, 15, 17, and the 7, 24, 25. Those allow you to do the work quickly and easily if you know those four, and then sometimes you don't even have to work anything out. Because on this first problem, I could have just said, well, this is a 5, 12, 13 triangle. So these problems are a little bit easier. We know that we have the cosine of theta is equal to 4/9, and we're looking for the secant, but we know that the secant of theta is equal to the reciprocal of the cosine of theta, and if I know the cosine, all I have to do is take its reciprocal, so that's 9/4, sorry. Likewise, I have the cosecant is equal to √7 over 2, and I want to find the sine, but I know sine of theta is equal to 1 over the cosecant of theta. Those are also reciprocals. Therefore, I know that 2 over root 7 is equal to the sine of theta, and I'm going to rationalize. So I have 2 root 7 over 7. Now let's review a little bit about special right triangles from geometry. We know we have 30, 60, 90s and 45, 45, 90s. Those are going to help us do some problems. In a 30, 60, 90, I like saying that the short side is equal to 1/2 the hypotenuse. And you can see that in this picture, because if the hypotenuse is 2a, then the side opposite the 30-degree angle, which is the short side, is half of 2a, right? And then the long side is equal to the short side times root 3. And you can also see that in this picture. Here is the long side opposite the 60-degree angle, and here's the short side opposite the 30-degree angle. So the long side equals the short side, which is a, times root 3. In isosceles right triangles, we know that the hypotenuse equals the side times root 2. And you can see that in the picture as well. Here's the side, and here's the hypotenuse, and the hypotenuse is the side root 2. So I want to find the exact value for sides, or for the sine of C, and it's a 30, 60, 90 right triangle. The sine of C is equal to the opposite over the hypotenuse. And in this case, we have the hypotenuse, but we don't have the opposite side. We know since we have the hypotenuse and we're looking for the long side equals the short side root 3, and I know the short side is equal to half the hypotenuse once again. So the hypotenuse is 22, the short side is half of that, which is 11, and this is 11 root 3 then. Therefore I can find my sine by taking the opposite over the hypotenuse. So the sine of C is the opposite, or 11 root 3, over the hypotenuse, which is 22, which reduces to root 3 over 2. I want to find the exact value of the cosecant of C in this case. Here's C, cosecant is equal to the hypotenuse over the opposite, because that's the reciprocal of sine. I have the opposite, but I don't have the hypotenuse. I know that the side root 2 equals the hypotenuse in a 45, 45, 90. So 3 root 2 is equal to the hypotenuse. Therefore, the cosecant is the hypotenuse, 3 root 2, over the opposite side, which is 3, and the cosecant is equal to root 2. So these next two problems are a little more like the problems we did in geometry. Here we have an angle, a right triangle, and a side given to us. The relationship is that this side is the opposite relative to the angle, and this is the hypotenuse, so we use a sine ratio because the sine is equal to the opposite over the hypotenuse. Therefore, we have the sine of 40 is equal to 2000 over the unknown x, and x equals 2000 over the sine of 40. X therefore will equal 3111.45 if we round, which makes sense because this is a smaller side than the hypotenuse because it's opposite a smaller angle, and that's bigger. Should always probably check that. We want to find the values of h and m. So in this case, relative to the angle 64, this is the opposite side, and this is the hypotenuse. We'll mix it up a little bit here. If I have the adjacent side of 25, then I can use a tangent ratio to find the opposite. So I'm going to say the tangent of theta equals the opposite over the adjacent. Therefore, the tan of 64 is equal to the unknown h over 25, and 25 tan 64 is equal to h, which gives me about 51.26 for the h value. And that also makes sense because this is roughly 26, so that's bigger than the side of 25, 51. Therefore, my hypotenuse better be bigger than 51. So now I can use sine or cosine to find the hypotenuse. I'm going to use the cosine because I have an exact value for the adjacent. So cosine of 64 is equal to the adjacent, which is 25, over the hypotenuse, which is m. So I have m equaling 25 over the cosine of 64. Therefore, m is equal to 57.03, which again makes sense because it's bigger than the 51, which is opposite a 64-degree angle. So we want to find the value of angle B, this angle right here, and we want to round this to the 100th. This is one of those things that you've probably forgotten from geometry. We have, relative to angle B, we have the adjacent side and the hypotenuse, which is a cosine ratio. So the cosine of B is equal to the adjacent 18 over the hypotenuse, which is 42. Now, if we want to get B by itself, we have to take an inverse cosine or an arc cosine. So I say B equals the inverse cosine of 18 over 42. Sometimes they call this the arc cosine, 18 over 42. And that's the button right above in blue on your calculator that says inverse cosine. We don't use the -1 button like an inverse for matrices, but there is an inverse cosine button right on your calculator. So you go ahead and press that, and you should end up with something around 64.62 degrees. Again, make sure your calculator is in degree mode. If you haven't gotten the values that I've received up to these points, your calculator is probably in a radian mode, and we'll talk about radians later, but you need to make sure your calculator for now is in degree mode. Alright, so Scott Farkas was trying to figure out the height of a tree. He determined the angle of elevation to the height of the tree was 35 degrees, measured the distance from the base and found it to be 10 feet, and we want to know the height of the tree. First of all, we got to understand what angle of elevation means. Well, pretend you got an eyeball, and that eyeball looks straight ahead. We call this the line of sight. Any angle you make that goes up is called the angle of elevation. While any angle you make in looking down is called the angle of depression. So, let's draw this picture. We got a tree, and we've got a guy 10 feet away, and he's making an elevation by looking up of theta, which is 35 degrees. and we're looking for the height of the tree. Well, notice we make a right triangle. We're looking for h. How do these two sides relate to that angle? Well, I have the opposite here, the adjacent here. So that's a tan ratio. I say the tan of 35 degrees is equal to the opposite, which is h, which we'll look for, or over the adjacent side, which is 10. So 10 tan 35 is equal to h. So h ends up equaling 7. So next we're going to want to find the angle of depression from the top of a lighthouse 250 feet above the water level to the water line of a ship 2 miles offshore. So let's draw this out. We've got some kind of a ship that is 2 miles offshore. Let's call this 2 miles. Let's call this a ship. And then you've got a lighthouse, and somebody looking down from that lighthouse to that ship, and he's making an angle of depression. So that's the straight line of sight. Our angle of depression is going to be here. Now, one thing you'll notice, again, we have a right triangle here, but this angle is not in that right triangle. Well, there's two ways to do this. You could drop an altitude down here, thus creating 2 miles up here, or you could say, hey, look at these guys. These are parallel lines, and alternate interior angles are equal, so this angle is also theta here. And we know that we have 250 feet as our height. Problem is now we've got a unit issue, alright, and we need to convert from feet to miles or miles to feet. Probably easier to go down. So we know if we have 2 miles, you can do dimensional analysis and say that there are 5,280 feet in 1 mile. So it's just a case of multiplying 5,280 by 2, which gets us 10,560 feet. So now we look at how these two relate. We see this is an adjacent, see this is an opposite. So again, that's a tangent ratio. Tangent of theta is equal to the opposite, 250, over the adjacent, which is 10,560. And again, we're looking for theta, so we're going to use our inverse. Of 250 over 10,560, and plug that into our calculator. And that's going to get us an angle of roughly 1.36 degrees. That's all we've got. Make sure you do your Connect Ed and your lesson summary, and we'll see you tomorrow.